Welcome. In this session, I will quickly outline two important properties of continuous functions. Recall that a function f is said to be continuous in an open interval if it's continuous at every number in that interval. But sometimes we want to talk about continuity over closed intervals, where we want to weaken the definition a little bit. The reason is that if I take a function like, say, square root of x times 1 minus x, it's defined only if x is between 0 and 1. So its domain is the closed interval from 0 to 1. Since it's not defined to the left of 0 or to the right of 1, I cannot talk about its two-sided limits at 0 and 1. But its graph, it turns out, is a nice graph, as you can verify by drawing it on your graphing calculator. It's a single continuous piece, so we should call it continuous. So we will adjust the definition of continuity over closed intervals by saying that a function is continuous over the closed interval from a to b if the limit at the endpoints from inside the interval equal the value. That is, at a we take the limit from the right, and at b we take the limit from the left. So we are staying inside the interval a to b at both of those. So of course, at every point or every number inside that interval between a and b, we should use the two-sided limit. Turns out functions which are continuous over closed intervals have a maximum value and a minimum value. We'll talk about how to find these values in chapter 13. Another important property of continuous functions is what's called the intermediate value property. If you have a function f which is continuous in the interval from a to b, and take a number y between f of a and f of b, then there is some number x in the interval a to b, so that f of x equals f of y. So in particular, if you have a continuous function which has both positive and negative values, it also has 0 as a value. So if you draw the graph of a function f of x, it's continuous, and you want to solve f of x equals 0, you can try to bracket that between two numbers where f has opposite sign values and try to shrink that. This is the method that calculator uses essentially to solve equations. Of course, this works only for continuous functions. For example, if you take the greatest integer function minus 0.5, it's negative at 0, positive at 1, but it's never 0 itself, because the greatest integer function can only be an integer, and so it cannot take the value 0.5. The intermediate value theorem also has another consequence that will be useful to us. It gives us an algebraic way of solving inequalities, because a function can change sign only where its value is 0 or where it's not continuous. So if you take an interval in which the function is neither 0 nor discontinuous, it's continuous over the entire interval, then f must have the same sign throughout that interval. We can just use a test point to identify that. We will do an example next time where we do this for rational functions, but in chapter 13 we will use this also for exponential and logarithmic functions. Since they are continuous, it also works for them. So I will stop here for now.